Hello everybody, my name is Alessandro Corbetta and I am a researcher at Eindhoven University of Technology. In this talk, together with my colleague Caspar, I'm going to present our recent work on benchmarking high-fidelity pedestrian tracking systems. This is a collaboration work together with Frank van Schadewijk from ProRail, Jasmin Thurau from SBB, and Joris Willems and Federico Toschi from Eindhoven University of Technology. This work is soon to appear also on Collective Dynamics. Continuous worldwide urbanization is putting higher and higher pressure on pedestrian infrastructures, such as train stations or airports. Additionally, in many European countries, it's forecasted that this pressure is only going to increase by even 30 to 40% in the next 10 years. So in this condition, it's mandatory to really understand what is the underlying physics guiding the crowd motion in such a way that we can design our environment in such a way that is best fit for the crowd flow. And of course, the first step towards understanding is measuring with the highest possible accuracy the trajectories of pedestrians. As of today, pedestrian tracking technologies operating in real-life conditions already exist. They typically leverage visual-like signals acquired by overhead sensors. Specifically, the most effective technology in this context uses depth map. These are measurement of the distance between each pixel of a scene and the camera plane. The typical output of this kind of sensors are grayscale fields like the ones that are displayed here, in which the color, in which the gray level represent distance. And so heads are the darker place, are the darker pixels, whereas the floor is reported in white. These kind of systems have been developed in academic settings to do fundamental research, but similar systems are already available for commercial purposes. Although these different systems share the same principle, the inner workings might be different, as well as the level of accuracy delivered, and even the type of data that are released by these sensors or this system as an output. This opens a number of questions, first of which is how accurate are these systems, and in general, how accurate is in the current state of the art, but also how reliable are new deployments of the same technology and how accurate are these in comparison to the best deployments, and even how can we compare future technology with respect to the current state of the art. To address all these outstanding questions, in this contribution, we propose a benchmark suite. This benchmark suite comprises 5 tests that are concise and simple to implement, and they aim at probing different aspects of pedestrian tracking that are relevant both in a scientific perspective, but also in a technological perspective. And now Cas will introduce the 5 tests, discuss the rationale, and also the results.
Thank you, Alessandro. The tests in our benchmark range from a more macroscopic level, testing crowd fluxes and density estimations relevant to facility managers, to a more microscopic level, testing position detection and trajectory accuracy, more relevant to science. Together with our benchmarking suite, we present the results of 2 state-of-the-art tracking systems, where the first tracking system is set up at the Eindhoven University of Technology, where we deployed 12 sensors in a 3x4 grid, covering an area of 150 square meters. The second setup is a commercial setup deployed at a real-life train platform, which consists of 3 commercial sensors in a 3x1 grid, covering 50 square meters. The first test tries to determine the accuracy in estimating crowd fluxes. So therefore, we ask participants to walk in an elliptical path, and we measure when pedestrians cross a vertical red line. Now we want to compare this estimated crowd flux to the ground truth crowd flux, so therefore we compare it to actual footage of the pedestrians. So we can see both footages next to each other, and we compare the number of pedestrians that crossed in both images. This test took the participants approximately 5 minutes. The Second test focuses at the global density estimation. Therefore, we defined an inner experimental area in which the number of pedestrians remains constant, while the pedestrians can move freely through the inner experimental area. We compared the number of pedestrians measured by the system to the ground truth number of pedestrians in the inner experimental area. The TOE setup reached 97% accuracy over the 5-minute test duration while maintaining a density of approximately 0.07 pedestrians per square meter, whereas the commercial setup at a higher density of 0.85 pedestrians per square meter reached an accuracy of 82%. In the third test, we want to determine how accurate a system can detect the position of pedestrians. Note, however, that it's hard to get a ground truth position of all pedestrians. Therefore, we want to ask participants to walk in straight lines. We ask them to do this multiple times, and their trajectories will appear as bundles. The width of these bundles should have a comparable width to typical head sway. And as we can see, the standard deviation in the width of these bundles is comparable to approximately 5 centimeters, which is the same as typical head sway. Additionally, we want to check for geometric distortions in the system. And because we know that the straight lines the pedestrians walked are parallel in the real world, we can check whether they are parallel in the recorded trajectories. So for instance, the distance between A and B should remain constant and should also be the same distance between C and D. Secondly, we can also check if the geometry has 90-degree angles as they had in the real world. We can see that both setups had an almost 99% accuracy for both geometric characteristics. In test 4, we probed the trajectory accuracy in a controlled environment. So we asked participants to walk from a certain origin to a certain destination. And because we know the origin-destination pairs, we can check whether the trajectory is continuously tracked without interruptions. And we can see here that the trajectories try to get very close to each other to reach very high local densities, as this increases the difficulty of the test. Now we can check the percentage of continuously tracked trajectories compared to all the trajectories. And we can see that the TOE setup with a large area of 150 square meters reached an accuracy of 73%, and the commercial setup with a 50 square meter area reached an accuracy of 77%. In test 5, we also probed the trajectory accuracy, but this time in a real-life environment. However, in real-life environments, we don't know the ground truth origin and destination of each pedestrian. Therefore, we define a domain in which it's very unlikely to see a trajectory originate or terminate. So this way, we can create three subsets of our data. The first one with a proper origin and destination, the second one with a termination at a place inside our inner domain, and the third subset is the trajectories which have an origin in the inner domain. And from these three classifications, we can determine the ratio between the continuously tracked correct trajectories compared to all the trajectories that have been recorded. We have only did this for the commercial setup, and this commercial setup reached an accuracy of 79%. To conclude, we have presented a lightweight and easily reproducible benchmark. We can use this benchmark to test the current state of the art. We can test new deployments of already used technologies. We can also test future technologies and compare it to the current state of the art. We've also presented the benchmark results of two state-of-the-art real-life tracking setups, which showed us that they are very capable of estimating crowd fluxes, estimating densities, and determining the accurate position of each pedestrian. Whereas the trajectory accuracy is still a bit lower, and this can be caused by very high local densities where the system is not able to accurately distinguish between two very close pedestrians, or this can be caused by stitching errors between neighboring sensors. Now I want to thank you for your attention and have a good day.